Hello, everyone, and welcome to Lecture 3 of the Mechanical Design course from AvengerRobotics. This lecture is part 2 to our lessons about basic physics. In this lesson, we'll go over torque, work and energy, and momentum. It may seem like less topics than last time, but these topics are really heavy compared to the last ones, and especially when it comes to the more complicated topics of physics. And I really want to spend more in-depth time with each individual topic. However, please keep in mind that teaching all of physics in merely 2 lessons is not good enough for most use cases. And therefore, I really want to emphasize that even after this lesson, we go on and try to learn more about physics. This is especially true for those who are going into AP Physics next year. It'll be very beneficial for you in order to truly get a full understanding of these concepts before we go in. So the first topic today is torque. So a recap from last time, we learned 2 essential topics that will be used in torque: Newton's 3 laws of motion and angular kinematics. If we combine these 2 subjects, we can understand torque. What is torque? Torque is the rotational version of force. Just as force causes linear acceleration, torque causes angular acceleration, or rotation, on an object. Torque is measured by the force perpendicular to the axis of rotation times the radius. So what do I mean by that? On this right, we have a lever on some axis that has a radius of 1 meter. So that means that the lever is 1 meter long, and we have a downwards force of 5 newtons. This force is perpendicular to that axis of rotation with that arm, and that's important. If that force was not directly downwards or directly upwards, only a portion of that force or a component of that force will be acting on the torque. The other portion will be going alongside that lever arm and will be doing nothing. So the torque here is 5 Newton meters. We get that by multiplying the radius, 1 meter, by the force, 5 newtons. So what is an axis of rotation? The axis of rotation is the point at which a rotating object rotates around. It sounds a lot of rotating going on here, but here's an example. So here we have another lever. And here in that yellow circle, we see an axis. That line going through is the axis of rotation. So when that force lifts the lever upwards, it is rotating around that point that is on the axis of rotation. So what is a perpendicular force? The force component that is measured in torque is perpendicular to the axis of rotation. So here we have a force that isn't perpendicular to the axis of rotation, and therefore we have to break it up into 2 forces, one of which, the yellow one, is. The easy way to do this is to use Pythagorean's theorem and basic trigonometry in order to see what lengths of this right triangle that is forming here are for each side. So the hypotenuse is the regular force. One of the longer side is the perpendicular force, and in this case, the shorter side is the parallel force, which we don't count in torque. Yellow is used for torque. Showing torque in free body diagrams. This is a simple example of a pulley. A rope is pulling the pulley on the right side. This will cause it to begin rotating clockwise. Notice how the arrow isn't in the center of mass anymore. Earlier, when we were talking about free body diagrams, the arrow was always pointing out of the center of mass. That's because that's the point all the forces are truly acting on an object. However, when there is torque, the force is not acting on the center of mass, and that causes a form of torque. You see, if it's not on the center of mass, that means it's rotating the object around. So here's an example of balanced torques. Similar to a block sitting still on a surface, there are 2 torques canceling each other out. This means the net torque is 0. So the torque on the right is currently trying to pull the pulley clockwise. Meanwhile, the torque on the left is trying to pull the pulley counterclockwise. Since they're both the same torques, they cancel each other out in the same way that a block that's sitting on a surface has a force of gravity or weight pulling downwards and a normal force pulling upwards. So in this case, the torques are balanced. Here's a more complex example. Although the left rope's downward force is lower, the radius is twice that of the force pulling clockwise. What I mean by this is that since torque is force times distance, or the radius, if the radius is larger, then the force has to be smaller to have the same torque. So currently, even though it doesn't look like the forces are balanced, since the largest force is half the distance of the smaller force, and yet the larger force is twice the amount as the smaller force, they are balanced. This is a second complex example. So the original pulling force was not perpendicular to the axis of rotation. Therefore, we need to break it down into components first. I'm sorry for this dashed line. It's not where it's supposed to be. I should have checked over this. But just imagine that dashed line was pointing to where the arrow is. So in this case, we see that the actual line is not fully perpendicular to the axis of rotation. It's kind of pointing downwards when it really should be pointing slightly down and to the right alongside the tangent of that circle. So if we were to break that up, it would now be pointing down the tangent of the circle and will show the actual force component that will be used in torque. So here's some more about torque. Just as force uses the equation net force equals mass times acceleration, torque uses net torque equals moment of inertia times angular acceleration. So on this screen, you can see what the variables and what they mean. I recommend you to write them down. Okay. So what is moment of inertia? Just as mass makes an object harder to gain linear acceleration, moment of inertia makes an object harder to gain angular acceleration. The closer the majority of the mass is to the axis of rotation, the lower the moment of inertia. So here we see we have two objects of equal mass. One of them is a ring, so all of the mass is on the outside of that radius. This is the hardest possible form of object in order to rotate. Versus over here we have a cylinder. This one, the mass is equally distributed all around. So this dotted line is actually the average of all of the mass. So imagine here that this second object is equivalent to a hoop or a ring like the other one, but of the smaller radius. In this sense, since the average mass area of the second object is of smaller radius than the left object, that means that the moment of inertia of the left object is greater than the moment of inertia of the second object. Disclaimer: finding the moment of inertia of an object is extremely complex. It uses a lot of calculus and other topics that honestly most high schoolers won't know how to do, and I'm not teaching today. So for now, we will therefore use known values for simpler shapes. The worst case scenario for moment of inertia is when the entire mass is a full radius from the axis of rotation. So for example, a light stick with a heavy weight at the end. In this case, the vast majority of the mass, the heavy weight, is all the way out at the end of the radius. Therefore, it will be the hardest possible thing to rotate. This type of problem uses the formula mass times the radius squared for the moment of inertia. All other formulas for moment of inertia is mass times the radius squared times a fraction that is less than 1. So for example, a cylinder might be 1/2 times mass times the radius squared. So here's an example problem. Let's say that there is a lever that is 1/2 meters long and an object with a weight of 5 newtons on its end. What is the net torque on this lever? I'll let you guys solve this on your own if you wish. Once you have an answer, if you wish, put them in the chat so I can see them. So here, all we have to do is multiply the radius, which is 1/2 of a meter, by the force that is perpendicular to the axis of rotation, which here it's nice and easy and just told us it's 5 newtons. So 5 newtons times 1/2 is 2.5 Newton meters. Here's another example problem. Let's say that there is a lever that is 1/2 meter long and an object with a weight of 5 newtons on its end. Assuming the moment of inertia is equal to 0.125, I just told you this to make it easy. What is the angular acceleration? Okay, so here it's 20 radians per second squared. If you remember from the first lecture in physics, the units for angular acceleration is radians per second squared, similar to how linear acceleration is meters per second squared. So math with torque. Remember the angular kinematic equations? Just like how force can be used with displacement, velocity, and acceleration, torque can be used for their angular counterparts. In robotics, we often use torque for mechanisms where the direction of the force remains constant throughout the change in angle. For an example, an arm. So when you're designing an arm in robotics, the main thing that is causing torque on your arm is gravity, and gravity is always going to be pointing downwards unless something has gone horribly wrong on your robot. So, in that case, we have to account for the fact that the torque would be constantly changing throughout the motion of the arm, as the actual force vector that is perpendicular to the axis of rotation changes as the angle of the arm moves. So in that case, all we have to do, typically for robotics, is find the worst case possible and the best case possible for torque, and see if our mechanisms can handle that. Questions? Okay, so someone asks, are you going to explain torque and pulleys? So currently I am at the end of explaining torque in this lesson, and that's because I don't want to go too in depth in any topic to be able to go over anyone's heads. Earlier, I kind of showed examples of torque being balanced in different ways and having a net torque. So if you really want to use torque and pulleys, just try to imagine how it would work in a regular Newton's three laws, F equals ma type of sense. You can also, research further into how to do this. If you wish to truly learn how to use torque in a more complicated sense using pulleys, you can come ask me. But essentially, the way a torque works in a pulley is that one of the torques is going to be greater than the other torque going downwards. So there'll be two torques, but one's going to be larger. And therefore, the net torque is going to be in one direction. Okay, let's move on. Section 2, work and energy. Work. What is work? Something is doing work on another object when it uses a force to move said object a non-zero distance. For example, a man pushes a box 10 meters with a force of 5 newtons to the right. So here in the bottom we have a box. With 5 newtons of force, it pushes 10 meters. Work is not done on an object by a force component that doesn't cause any displacement. That might seem kind of complicated to understand, but here we can see a box with has a weight down and an angle going upwards being pulled. Maybe this is a rope of some sort and dragging across the ground. So this force going up to the right can be broken down to two forces, one of which going up, one of it going to the right. Since the box is only moving right, only the right pointing arrow does work. So what's some math for work? Work is mathematically defined with the equation work equals force times distance. Work uses Newton meters as its unit, which is called a joule. Here's a note. Even though it uses the same unit as torque, torque is fundamentally different than what work is, and therefore work, when you're using Newton meter, is called a joule, but for torque, it's not. It's a somewhat complicated question I went into a deep dive research on earlier. However, torque is not the same thing as work. However, they use the same unit. So a block being pushed 10 meters with 5 newtons will have received 50 joules of work. Once again, force times distance, 10 times 5. So here's an example problem. An object with a weight of 10 newtons is in free fall. If the object travels 20 meters before it hits the ground, how many joules of work did gravity output? Okay. So here we can see that 10 newtons times the 20 meters that it falls equals 200 joules of work. If it's hard for you to understand this, remember that the weight is the force that gravity is asserting onto any object at a given time. So since it's in free fall and it's going straight downwards, the weight, 10 newtons, is being used for the total 20 meters, which causes it to be 200 joules of work. Here's another example problem. A robot moves itself with 5 newtons of force forward for 5 meters. How many joules of force did the robot output? Okay, so just like before, we multiply the force by the distance. 5 times 5 equals 25 joules of work. Nice and easy. So work in simple machines. You may have learned about simple machines like ramps, levers, pulleys, and gears before. These all take advantage of work. If you need to exert a certain amount of work on an object, for example, moving a heavy object up a certain distance, you can reduce the required force by increasing the distance. This is also a concept called mechanical advantage. So here's an example problem. You need to move a 10 Newton block up 2 meters of height. What length does a ramp have to be so that you can only have to push the block with 2 newtons? So here we see this is a bit of a slightly more complicated question, still relatively easy, but requires 2 steps. So first we realize that 10 newtons times 2 meters is 20 joules, so we need a total of 20 joules of work to move this block up 2 meters. So now if we want to only use 2 newtons of force to do the same amount of work, we have to divide the work done, which is 20 joules, by 2 newtons. And that way we get the distance required, 10 meters. What is power? Sometimes it is necessary to know the rate at which work is done. For example, a motor has the capacity to exert a certain amount of work per unit time. This is called power. Power equals work divided by time. This is measured in watts. So if you ever looked at a motor and you realize they can output a certain amount of wattage and power, sometimes they might use that. That's essentially just the work per unit time. Energy. What is energy? Energy is defined as the ability to do work. There are many different types of energy: potential energy, kinetic energy, thermal energy, electrical energy, chemical energy. There's so many different types of energy. For this course, there are only 3 that are important: potential energy, kinetic energy, and thermal energy. Just like work, all energy is also measured in joules. Potential energy. The energy that is stored due to the relative position of the object in a system. So, once again, scientific terms, no one knows what this means. So, in this case, we'll use an example. A ball being held up high in the air has gravitational potential energy due to the potential for gravity to do work on the ball. So, when you hold a ball up high in the air, there is the potential, if you were to drop the ball, for gravity to do a certain amount of work on that ball in the future. That is called potential energy. There are other forms of potential energy, but it's too advanced for this course. So here's the math for potential energy. The equation for gravitational potential energy is as follows. U of g, which is the symbol for this, equals mass times g times height. So once again, m equals mass, g equals acceleration of gravity, h equals height. Note, this is a simplified version that assumes a constant acceleration of gravity. For robotics, this is completely fine. We're staying on the surface of the Earth. If we were making a satellite or a rocket, we might want to use different forms because as we get farther from the Earth, the value for g decreases. And therefore, the gravitational potential energy will also change. So kinetic energy. The energy which an object possesses due to being in motion. For example, a marble being dropped on a track has UG that turns into movement. So it has a certain amount of gravitational potential energy. Gravity does work on that marble, and it has a certain amount of velocity due to that work. Now that velocity can then be transferred back into gravitational potential energy because it goes up a ramp, goes into the air, and then eventually it stops midair before it falls down again. So all of that kinetic energy, that energy from it being in motion, turns back into potential energy. There can also be both translational and rotational kinetic energy. A ball that is spinning a certain angular velocity also has energy due to its motion. So, let's say a block sliding on the ground, without rotating, has translational kinetic energy, while a ball rolling down a hill has both translational kinetic energy and rotational kinetic energy. So what's the math for kinetic energy? The equation for kinetic energy is as follows. K translational, which is translational kinetic energy, equals 1/2 times mass times the velocity squared. Rotational kinetic energy equals 1/2 times the moment of inertia times angular velocity squared. So just like everything else with angular, it's going to be the translational version and the angular version. They both are the fundamentally same formula. It's just you replace the linear variables with the angular variables. So thermal energy, the last one important to us today. In mechanics, thermal energy is the heat, sound, and other environmental factors that is caused by an object moving or going through friction, the like. This is most obvious with friction, though, where it turns kinetic energy into thermal energy in the form of heat. So, if you have something going really fast and it slides across the ground with a lot of friction, it's going to create a lot of heat. That is going to absorb energy from the system. This can account for the law of conservation of energy, as we will learn shortly. Conservation of energy. We won't go over all of these, but there is a couple laws called the laws of thermodynamics, which essentially go over what happens to energy inside of systems. So the first law of thermodynamics, which is the most important to this course, states that energy cannot be created or destroyed within a closed system. What does a closed system mean? A closed system is a system in which there are no external forces. So let's say, you have a car, and that car is adding, an external force to everyone inside of that car. So if there's something happening in that car, there is an external force on the system with the car pushing. But on the planet Earth, as long as we don't, talk about the sun and the solar system and stuff, it's easy for us to assume that there is nothing really externally happening there. So as long as there's no direct external forces on a system, we can consider it a closed system. Therefore, the total energy in that system will remain the same. So finding thermal energy. We can find the amount of thermal energy released in a system by finding out the difference between the initial mechanical energy and the final mechanical energy, due to the law of conservation of energy. Now, I didn't define this before, but the term mechanical energy essentially is just a combination of potential energy and kinetic energy. We use this mostly because it's easier to find thermal energy. If we differentiate kinetic and potential energy, we can find out what is the total energy loss in the system when we don't account for potential and kinetic energy by just subtracting the initial and final, and we can say, well, that must have been lost to thermal reasons. So the connection between work and energy. There is another definition of work which I didn't share earlier. Work is the measure of the transfer of energy. Essentially, whenever work is happening, energy is being transferred from one type to another in a system. For example, from a gravitational potential to kinetic through the work done by gravity. So here's an example problem. There is a 0.5 kilogram object being dropped in the air. Assuming air resistance is negligible, which means just assume it doesn't exist, and that all potential energy transfers to kinetic, how fast will the object be moving after 6 meters? In this case, g equals 10 meters per second squared. Okay. So here we need to find the initial potential energy of the object, and we use the potential energy, gravitational potential energy equals mass times gravity times height. So the mass of the object is 0.5 kilograms times g, which is 10 meters per second squared, times 6, which is the height, equals 30 joules. So now we have to recognize that all of those 30 joules are now going to be transferred to kinetic energy. So we rearranged the kinetic energy formula for V. We get V equals the square root of 2 times the kinetic energy divided by the mass. Now we can plug in the known values to solve. So if we plug in all the values, and hopefully you have a calculator when doing this, you get 10.95 meters per second. Here's another example problem. There is a 0.1 kilogram ball that is thrown straight up into the air at 10 meters per second. What will be the maximum height of the ball in meters? Once again, g equals 10 meters per second squared. So first, we need to find the initial kinetic energy of the ball with k equals 1/2 times the mass times the velocity squared. So here we have the mass of 0.1, the velocity of 10 meters per second, and we multiply it by 1/2. So we just do the math here. We find out that it's 0.1 times 100, which is velocity squared, and we divide it by 2. That all together gets 5 joules. So that's the total kinetic energy at the start of the scenario. So now, we then need to rearrange the gravitational potential energy formula for height. So UG equals mass times g times height. So if we arrange the math for height, we get height equals the gravitational potential energy divided by the weight, or mass times gravity. So we can plug in the known values to solve. So here we have the 5 joules from earlier, which will be all transferred to gravitational potential energy. And we can just divide it by the weight, which is going to be around 1 Newton, because it's going to be 0.1 times 10. And if we do the math there, we get 5 meters. So that is the total height. Any questions? So someone earlier in chat asked, what does the letter UG means? So in physics, I don't know what exactly happened, but someone in the past decided that the letter U is going to be the letter we use for potential energy. I don't know why. There probably is a really good reason, but someone in the past decided that. So U sub G is just the variable for gravitational potential energy. Someone also said, at what point does the object stop accelerating? So once again, if we go back to the first lecture, an object accelerates because there's a net force on said object. So if an object is in free fall, it's going to keep accelerating until it collides with the surface, in which case it'll have a normal force that will cause the object to be in a balanced state and therefore not have a net force. Someone also asked whether or not we square the velocity. Yes, in the kinetic energy formula, it is 1/2 times mass times the velocity squared. So in this case, the kinetic energy is proportional to the square of the velocity. So if the velocity is going 10 meters per second, in the formula, you will be plugging in 100. Once again, both of these lectures will be going on YouTube. You can rewatch them. You can also ask me any questions about these subjects you wish outside of these lectures if you are on Slack, if you are watching this later. I'm not going to promise anything, I'm sorry. But you also have the entire internet at your fingertips. The point of this is just to, throw a bunch of different topics at you all, just so you have a slightly easier understanding of learning these later. Okay. Momentum, the last major topic for today. What is momentum? Honestly, it's a very difficult concept to imagine. I could not just tell someone exactly what it is. But instead, I'll use an analogy, which is the thing in which us kids in robotics like to talk about the most. Sports. We love them. We love going outside. We love playing sports. And we love touching grass. So during any type of sporting event, it is common to see one team to start dominating. As they continue to succeed, they become more intimidating and it becomes harder and harder to stop them. So when little Jimmy and his little league team goes on to hit, 20 home runs in a row, as it does happen, they're all super, super happy. They're all stoked. They're winning like crazy. Nothing can stop them. However, the other team, the other team just hit 15 home runs in a row. Oh, yeah, not a good time. So now it's very hard to stop that team that just did really, really well. In spoken English, we call this momentum. We say, oh, that team has momentum. And honestly, it works the same in physics as well. In the same way in which those teams are harder to stop, momentum in physics is just how hard it is to stop an object. So using math, the momentum is defined as the mass times the velocity. This shows that either as the mass or the velocity increases in an object, the difficulty of stopping it, or, essentially its momentum, increases as well. The symbol for momentum is P for linear momentum, L for angular momentum. So change of momentum. Momentum can be changed in an object through an acceleration causing a change in velocity. This requires a force to be exerted on an object with a duration of time. So if you don't understand that the first time, essentially what happens is that momentum is mass times velocity. Changing an object's mass is pretty difficult, so most of the time when a momentum changes, it's by changing the velocity, which requires acceleration. That acceleration requires there to be both a net force and a certain amount of time that net force occurs just so the velocity changes. So this relationship between force and duration, or the amount of time that force is exerted on the object, is called impulse, or F times t. Impulse is the same as the change in momentum. So with momentum, there's this thing called the impulse momentum theorem. It's a lot of complicated math. Essentially, what it means is that the force times the time that force is applied is equal to the change in momentum on an object. So for now onward, impulse's symbol is J. Once again, I do not know why it is J, it just is J. So here's an example problem. If a cart is 5 kilograms and is moving at 5 meters per second, what is the momentum of the cart? Okay, so here, very simple problem. All we have to do is multiply the mass times the velocity to get 5 kilograms times 5 meters per second. So, in the time of just multiplying things together and, multiplying the units together, in that formula, we get 25 kilograms times meters per second. So in this case, multiply the kilograms and meters per second, we get the unit for momentum, kilograms meters per second. Super long, I hate writing it, but that's what it is. Sadly, it doesn't have an easy name like joules just to say. Super easy math though. So here's another problem. If a cart is at rest and 5 newtons of force is applied over 10 seconds, what is the change in momentum? Okay. So if you remember the impulse momentum theorem I said earlier, you realize that impulse is equal to the change in momentum. And impulse is equal to the force times the duration. So here we just have to take the force, 5 newtons, and multiply it by the duration it was occurred over, 10 seconds. So therefore we can get 50 newton seconds, which is the unit for impulse, which can then just be converted directly to 50 kilogram times meters per second. I'm going to make a new candy bar called 50 gram. It'll be delicious. So now we have to talk about conservation of momentum. Every system has a certain amount of momentum within that system. And if there are no external forces on that system, that amount will be conserved. What does this mean? So let's say we have a system, it's a complicated subject, but essentially it's just two objects floating in space, completely still, at rest. If you took the center of mass, or the average position of mass of both of those objects, you'll have the center of mass of the system. Now, if both objects are at rest, that center of mass of the system is going to be completely still as well. Now, if you take the total mass of that system times the velocity of the center of mass of the system, you get the momentum of the system. You can also get that by adding the momentum of each individual part of the system. So in this case, it'll be 0 plus 0 equals 0. However, if you have, let's say, one object collide into another object, but there's no actual external forces, the total momentum of that system will always remain the same. In the same sense, the center of mass of the system will always maintain its same momentum. So, like I said earlier, there's collisions. A collision is when one object strikes another object. When the objects collide, momentum is transferred between them. However, like I said earlier, due to the conservation of momentum, if no external forces act on either object, the system's momentum will remain the same. So here's an example. If a cart on a track runs into another identical cart on that track that is at rest, and the second cart gains the same velocity as the first cart, then the first cart must have completely stopped to conserve the system's momentum. Because since the masses are the same, the first when it hits and all of the velocity has to go into the other one in order for the velocity of the second one to be the same. However, this does not mean that every single time a cart strikes another cart that it will completely stop and the next cart will have the same velocity. This is just an example. So now we have to talk about elastic versus inelastic collisions. In some collisions, mechanical energy, so kinetic and potential energy, will be conserved as well. These are called elastic collisions. During some collisions, mechanical energy will be lost into thermal energy or deformation, and those are called inelastic. And then there'll be some collisions where, let's say you have a dart that hits a board and it just completely stuck together now. Those are called perfectly inelastic. So some collisions you might go through, some collisions you might bounce back. Those are typically inelastic collisions or elastic collisions, but if they stick together, they are perfectly inelastic. There is some equations and math you can do with these. Too complicated for today. If you want to know more about them, please contact me later. I will be glad to share them. So now we can talk about explosions. An explosion occurs when two objects push off of each other and start moving in opposite directions. Down in the bottom right corner, we see a very, Hollywood example of explosions. But, typically when we talk about explosions in physics, that's not what we mean. What we mean more so is when two things push off each other with either some stored energy, like in this case, chemical energy, or a spring, or just two people pushing each other away from each other in a frictionless plane. In those cases, since both objects assert the same impulse on each other, which is, force times time, which is equivalent to change in momentum, their momentums would be equal and opposite, and therefore, if you add them both together, would equal the same initial momentum of the system. Essentially, during an explosion, since there are no external forces, momentum is still conserved. Conservation of momentum continued. Explosions and collisions show how momentum can be used for mechanical design. We can take advantage of our knowledge of momentum in order to manipulate objects. Here's a really good example of momentum manipulating objects. Momentum can also be used with moment of inertia and angular velocity. This is angular momentum, which is used as the symbol L. This is especially important for mechanisms meant to shoot objects in the air with wheels, as the angular momentum can transfer to linear momentum. So here in the bottom, we have a scary little equation. Moment of inertia times the angular velocity, which is the angular momentum formula, just like mass times velocity, equals mass times velocity times L. And L is the distance from the angle of rotation. Axis of rotation, not angle of rotation. So L is similar to what the radius would be in a torque formula. In this case, we can transfer the momentum of an angular moving object, like a wheel, to a linear object. So an example problem here is if a flywheel loses 2 kilogram meters squared per second, and that's the unit for angular momentum, when shooting a ball, what is the speed of the ball? Assume the ball is half a kilogram and the distance is 0.1 meters. Okay. So here we have to use the equation, which I so thoroughly went through my presentation to write as equat. The change in angular momentum equals mass times velocity times L to solve, and we have to solve for V. So we change that formula around, we get V equals the change in angular momentum divided by mass times the length. So if we take the equations we got, we take the values we got earlier in the question, we get 2, which is a change in angular momentum, divided by the mass, which is 0.5 kilograms, times the length, which is 0.1 meters, to get that ball will now be moving 40 meters per second. Questions? So someone in chat asked, could you explain the ice skater extending arms out versus bringing them in, then using the concepts we learned today? Yes, that's the perfect example of angular momentum. So, angular momentum, which remains constant if there's no external forces, or torque, and angular momentum, which remains constant assuming no external torque, is the moment of inertia times the angular velocity. So an ice skater who's spinning around in a circle, if they have their arms all the way out, their moment of inertia is pretty high because they have the mass of their arms, all the way out to their sides. It brings the average point of their mass outwards. So if they have a certain amount of angular velocity there, they'll be spinning around. Now, when they bring their arms in, they will be lowering the moment of inertia by bringing more of their mass inwards towards the part they're spinning around. And when they bring that area, the moment of inertia lower, in order to maintain the same exact angular momentum, they have to increase the other variable, which is the angular velocity. So as the moment of inertia decreases by bringing their arms in, the angular velocity of the spinning ice skater increases and they start spinning faster. That's how ice skaters control their spin. Another great example of this is cats trying to, jump to the ground. They purposely will curl up and decurl their body in order to change the rate at which they're spinning in order to make sure that they always land feet first. A lot of nature already understands the concept of momentum better than we do. It is very funny. So another question is, what makes objects and materials better at transferring momentum? This is all what you're trying to do in desire with transferring momentum. Certain materials, when they collide, will cause certain different types of collisions. Sometimes they'll go through, sometimes they'll bounce. In general, if you're trying to make things bounce off each other, you want to make more elastic materials that are likely to cause more of a springing sensation. If you're trying to make things like kind of stick together and have a more perfectly inelastic collision, you want to use materials that deform very easily. So things like clay or other like materials that would actively deform when they collide. So someone in chat said, because the closer the mass is to the center, the I is lower and less resistance to the change from inertia. Yes. So whenever the mass is closer to the inside of your body and you're spinning around the center of your body, your moment of inertia, or the kind of like the radius of your average inertia of your body, comes closer to the axis of rotation and therefore decreases the moment of inertia and makes your body easier to spin. So they also asked, what about steel balls and Newton's cradle? So steel balls work because the steel in those balls deform very little. So even though it doesn't look like they're elastic in the same way a spring is, the tiny little collision actually completely not completely, but transfers the vast majority of the energy in that ball, and therefore the momentum. It transfers most of the energy of the ball and most of the momentum in the ball into the next ball, and it keeps on going. So kind of like a spring, the steel ball deforms just a tiny little bit, but then it springs back out again. It's not permanently deformed. It's actually an example really close to a elastic collision. Not exactly there, still a little bit of energy loss over time, but it's really close. Remember that in real life, there's a lot of problems that are caused due to air resistance, friction, sound, just a bunch of lost energy, lost momentum over time. If this was in a vacuum, the momentum would be perfectly conserved in a Newton's cradle. Any more questions? Just to let you know, this is the last question section of the whole presentation. We're almost done. So if you have any questions about any other sections you want me to go over, this is also the time. So final thoughts. I have had a really difficult time making this lecture today, and also the previous one, because physics is a topic that's very special to me as a person. I really wish I can spend an entire summer course worth just talking about each of these subjects really in depth and try to really help you get a full-on understanding of this. But I gotta realize that physics, while essential for mechanical design, so much so that we devoted a whole third of the whole course to it, is not the only topic we can go over. If there's any topic in which I want someone to have a somewhat minimum basis for understanding, it's physics. But I don't need someone to know exactly how to solve every single problem in physics just to be able to design a machine. The purpose of this course, specifically the sections of physics, is to allow you to understand enough about physics that when you hit questions, when you have challenges in physics, when you're designing your machines, your robots, anything, you have enough knowledge to understand the words and the vocabulary and the concepts that you need to know in order to research yourself what these problems are. So as you go on your course of, through engineering, through mechanical design, through robotics, you'll encounter a bunch of physics problems along the way. And I hope this course teaches you enough in order to understand where to start. So even though this course both seems not fruitful enough to fully understand the subject and a little bit too fast to truly understand what I have been taught, the purpose of this is just to throw ideas into your head, to let you know what these things are. So now when I say torque, you have a vague understanding of what it is. When I say forces, you understand what they are. When I understand a difference between velocity and displacement and acceleration, you can at least have an idea in your head what those are. So now when you're answering these problems in real life scenarios, you have a place to start. That's the purpose of this course. And I think that is a really good time to end off today's lecture. See you guys next week.